Welcome to structural dynamics class. So in this class we will study how to apply the continuous systems principles and solve say real world problems. So these problems could be in many ways. Say one is like say a tower is vibrating because of wind, or a cantilever beam is vibrating because of say some force. So you can assume that a diving board of a swimming pool and a person is jumping on that, okay. Or maybe a seating arrangement, a platform or seating arrangement at the slab in a stadium where people are sitting on the slab, and then in excitement of seeing match, so they may do jumping on this one. So when they sit, it is a static load, but when they jump on it, then it is a dynamic load. So how this static deflection and dynamic deflection are related? So these are all real world problems. So how do we solve this real world problem? Using principles of continuous systems. So this, suppose let's take an example of the slab itself, a seating arrangement in the stadium where mass is continuously distributed, people load is also continuously distributed. Then how do we solve this problem? I am formulating here a problem, okay. So before that, let me explain you what is the equation of motion for continuous systems. So equation of motion for continuous system is same as mu double dot cu dot plus ku is equal to p. So in this case, m is a generalized mass because it is not lumped at one location. So we need to take into consideration the shape function, which is a deflection profile of the member or the structure. All that need to be considered. So that's why we call it as generalized mass. Z double dot is acceleration, C tilde is generalized damping, Z dot is velocity, K tilde is generalized stiffness, and Z is a displacement function. P tilde is also generalized force. Now how do we get these generalized properties? From the given structural properties, say given structural parameters. So what are the parameters of the structure? Geometry property, material property, and end conditions. Three things are there. So if you look at this one, m tilde, we can get integral of 0 to L, that length, m of x. So if mass is varying according to length, so for example in this case, so density, that mass is higher at this location and slowly it is cross section is getting reduced. So that means what? Mass is reducing here, mass. So that's why mass also can be a function of x. So mx into psi x whole square. What is psi x? Psi x is a shape function, or we can also call it as a displacement or deflection profile, and then dx. So integral over the length will get the generalized mass. Generalized mass means if this continuous system has to be made equivalent to a single degree of freedom system, what will be its mass? So that is m tilde. Then similar to that, we have generalized damping value. So damping value present at every location, and then psi x square dx, this is generalized damping. Similarly, we get generalized stiffness. So stiffness again 0 to L ei psi double prime x square dx, this is generalized stiffness, and also generalized force, that is px psi x dx integrated over 0 to L. So we have generalized properties. So generalized force, generalized stiffness, generalized damping, and generalized mass, all these we have. Now let us go into the application. So how do we make use of this and then solve the problem? Now the problem is, as a structural dynamics engineer, I am asked to design a seating arrangement of a stadium. Typical seating arrangement has the form of steps from lower level to higher level supported on the stringer beam. The span length between two beams is, two supports is 11.7 meters, and then properties of the T section. So that means the cross section of the beam is T. So that means density is given as 2400 kg per meter cube. Area of cross section 0.1587 meters square. Moment of inertia along its x axis is 6.327 into 10 to the power of 7 meter power 4, and then modulus of elasticity 3.7 into 10 to the power of 6 kilonewton per meter square. So using these properties, we need to find the deflection, that is maximum deflection. So check the safety of cross section if the people standing on it are applying load of 0.4 kilonewton per meter square with a frequency of 3 hertz. So now how this 3 hertz is coming, let me explain you that. So this is the property. So people are sitting on that. It is something like sitting arrangement is something like this. So we are talking about this one, this. So this along this direction, along this direction. So this is what we are talking. Okay. So this beam is supported here, supported here. So that is the beam. So now if I take the cross section of that is a T, yeah, it is something like this. Okay, T section. Now people are standing here. As I told you, in excitement, they are jumping, stamping, clapping, all that. So that is generating a harmonic motion of 3 hertz. So now we need to put this into, say, mathematical form. So now step 1, let us first find out the applied force. So we already know that applied force, that is generalized applied force, is integral 0 to L Px dx. This is generalized applied force. So that value is say 0.4 kilonewton per meter cube is given. So I am using that 0.4 into 10 to the power of 3 into 0.762 sine 6 pi t into psi x. Okay. Oh, so in this one there is psi x term also. Psi x. Okay. So this is a force which is applied sinusoidally. Okay. Then psi x dx. So all put together we are getting this value 713.23 sine 6 pi t. So 6 pi is the forcing frequency. Then step 2, let us find out natural frequency of the system. So for finding natural frequency of the system, we need k, we need m. So under root k by m is a natural frequency. So let us first find out what is, say, m, mass of the system. So mass of the system is m into psi x square. So psi is given as, psi is a deflection profile. Deflection profile is given by this function. So psi x is equal to x by L 2 into x by L cube plus x by L to the power of 4. So this need to satisfy the boundary condition. So at x is equal to 0, psi is equal to 0. At x is equal to L, psi is equal to 0. So then what we get is, you can see this one, x is equal to, this becomes 1. So this becomes 1, this becomes 1. So 1 minus 2 plus 1 is 0. So at x is equal to L, this is satisfying, and at x is equal to 0 also it is satisfying. So now what we get is mass. So if you substitute this one in this one, so 326.6 kg is the mass. And then we need to use x double prime term in calculation of stiffness. So now calculation of stiffness, we get like this. EI is known value, psi double prime we derived it in the earlier slide. So what we get is K is equal to 701,589.7 Newton per meter as a generalized stiffness. So generalized mass we calculated, generalized stiffness we calculated, and then what we get is omega is equal to under root k by m. We substitute value of stiffness and mass. So generalized mass, generalized stiffness, we get 46.35 radians per second. Then we get R, that is frequency ratio, omega and 6 pi by this one, we get 0.407 is frequency ratio, that is R. Now the maximum deflection at midpoint. So for that, let us look at the steady state deformation due to harmonic force. So we have two displacements, that one is complementary function and another one is particular integral. So we are more interested in particular integral because this gives the maximum deflection. So Zt is equal to Z0 sin omega t minus phi with phase. So Z0 is the amplitude. So P naught by K RD, this we already know. Okay. So you can refer to single degree of freedom systems maximum dynamic amplification factor lecture. So now Z max is sinusoidal part will disappear. Maximum value of this can be plus 1. So if we remove that, so we get Z max is equal to P0 by K RD. So RD is, we know that 1 by 1 minus R square whole square plus 2 zeta R whole square. Now if we substitute R value in this one, we get 1.1988 is RD. Then maximum deflection at midpoint. So maximum deflection at midpoint is, so this is according to deflection profile, we get 0.375. So in deflection profile equation you substitute L is equal to, so x is equal to L by 2. So then we get 0.375. Then maximum deflection will occur at say peak value of z and at L by 2. So that means what, psi at L by 2, P naught by k Rd. So P naught by k into Rd, if you substitute these values, P naught by k Rd value and psi is equal to L by 2 value, if you substitute, finally what we get is 0.38 millimeter as the deflection because of the loading applied by people in dynamic manner. This is the maximum deflection. So we need to check whether this is less than or equal to allowable deflection by using like first fundamentals of IS 456 limits. Okay, by using limits of IS 456. Okay. Now steady state acceleration due to harmonic force. So that is acceleration is equal to minus omega square z0 sin omega t minus 1. It is only 2 times differentiation of z, we will get this value. So if I substitute that value, amplitude of vibration is equal to, amplitude is 6 pi square into P naught by k, that value is Rd into P naught by k, that is 3.805 into 10 to the power of minus 4. So maximum acceleration is 0.135 meters per second square. So we have found out acceleration, we found out displacement. If we check if it is whether it is less than the specified limits or more than the specified limits, we will get whether the structure is safe or not. So in summary, what we have discussed in this class is a application of continuous systems. So in continuous systems we write generalized equation of motion and then we find out properties such as generalized mass, generalized damping and generalized stiffness and as well as generalized force. So again, by using the fundamentals of a single degree of freedom system, we can find the maximum deflection, maximum deformation using the same principles by using generalized properties of the structure.